Hello dear students, I am Latarani HM, Assistant Professor of Mathematics. Today I explain the topic alternating series. In the previous classes, you learnt about positive series. In positive series, we find the nature of the series by using comparison test, D'Alembert's ratio test, Rabi's test and also Cauchy's root test. Now we learn what is the alternating series and how to find the nature of the alternating series by using the Leibnitz test. First we define the alternating series. Alternating series means a series with terms alternatively positive and negative is called an alternating series, or this can also be defined like that: a series u1 minus u2 plus u3 minus u4 plus so on, where un is in a positive terms is called an alternating series. This can be written as, the alternating series can be written in the summation form, that is summation n is equal to 1 to infinity minus 1 to the power of n minus 1 into un. For example, consider 1 by 2 minus 1 by 4 plus 1 by 8 minus 1 by 16 plus so on. This is an example for the alternating series, because here we have the alternative sign plus minus plus minus. Therefore, this is an example for the alternating series. Consider one more example, that is 1 minus 1 by 2 plus 1 by 3 plus 1 by 4 minus 1 by 5 minus 1 by 6 plus so on. This is not an alternating series, because here all terms are not a positive and also all terms are not a negative terms, and one more, it is not an alternative sign also. Here plus sign is there, here minus, but in third and fourth we get the positive sign. Therefore, this is not an example for the positive series and also an alternating series. Leibniz test. This test is applied to find the nature of alternating series only. Statement: the alternating series. The alternating series is u1 minus u2 plus u3 minus u4 plus so on. The alternating series is in a convergent if un is greater than un plus 1 for all n, and limit n tends to infinity un is equal to 0. Means Leibniz test means the alternating series is in a convergent, it satisfies the two conditions. What is the condition? Un is greater than un plus 1 and also limit n tends to infinity of un should be a 0. If two conditions are satisfied, then the alternating series is in a convergent. Otherwise, it is in a not a convergent. Proof: let us consider sum to n terms with the nth partial sum of the series minus 1 to the power of n minus 1 into un. This is an alternating series. Sum to n terms. Expand the summation. After expansion, we get like that: u1 minus u2 plus u3 minus u4. Sorry, this one is plus u5 so on, minus 1 to the power of n minus 1 into un. Now, this is the sum to n terms. Now, write the sum to 2n terms. Sum to 2n terms are u1 minus u2 plus u3 minus u4 plus so on, u2n minus 1 minus u2n. Now, write sum to 2n plus 1 term. Sum to 2n plus 1 term is nothing but sum to 2n terms. Along with that, we have 2n plus 1, that is u1 minus u2 plus u3 minus u4 plus so on, u2n minus 1 minus u2n plus u2n plus 1. From u1 to u2n is nothing but s2n. Now consider s2n plus 2. s2n plus 2 is nothing but u1 minus u2 plus u3 up to plus u2n plus 1 minus u2n plus 2. Now consider S2n plus 2 minus S2n. Sum 2n plus 2 terms and sum to 2n is equal to, this will be cancelled. Remaining is U2n plus 1 minus U2n plus 2, which is greater than or equal to 0 because of the first condition. In the first condition is Un is greater than Un plus 1, means U1 is always greater than U2. Therefore, here U2n plus 1 is greater than 2n plus 2. Hence, it is will be greater than 0. Hence, yes, 2n plus 2 minus S2n is greater than or equal to 0. That represent S2n is monotonically increasing. Also, consider S2n elements. S2n element is U1 minus U2 plus U3 up to minus U2n. Now rearrange the series. U1, here we take minus sign outside, we get U2 minus U3. In these two terms, take minus sign, U4 minus U5 plus so on. Again, take minus as a common, then we get U2 minus U3 plus U4 minus U5 plus U2n minus 2 minus U2n minus 1 plus U2n. Again, from the first condition, this is greater than 0. That is, Un is greater than Un plus 1. That is, Un is greater than 0. Hence, sum to 2n terms is less than or equal to first term U1. Therefore, the sequence S2n is bounded above. If the sequence S2n is monotonically increasing and bounded above, then it is in a convergent. Hence, we conclude that sum to 2n terms is converges. That means limit n tends to infinity, S2n is equal to L, where L is in a finite quantity. Similarly, we can prove that S2n plus 1 is also a convergent. Therefore, consider limit n tends to infinity of S2n plus 1. What is S2n plus 1? In the previous slide, we know that S2n plus 1 is nothing but S2n plus U2n plus 1. Now apply the limit n tends to infinity to this function. Limit n tends to infinity of S2n is in a L, and limit n tends to infinity of U2n plus 1 gives 0 because of the second condition, that is limit n tends to infinity of Un is equal to 0, then U2n plus 1 is also gives the value as 0. Therefore, the sequence sum to 2n terms and sum to 2n plus 1 converges to the same real value L. Therefore, the sequence sequence Sn converges to L. Hence, the given series is convergent. This is the proof of the Leibnitz test. The alternating series will not be convergent if any one of the two condition is not satisfied. Any one of the condition means we have two conditions, that is Un greater than Un plus 1 and limit n tends to infinity of Un is equal to 0. Among these two conditions, if any one is faced, then given series is not a convergent. And two more definitions are there, that is absolutely convergent and conditionally convergent. The alternating series is said to be absolutely convergent if the series of positive terms, positive terms means Un are positive. The series of positive terms, that is summation n is equal to 1 to infinity mod of Un. Mod of Un means all are positive terms, is a convergent. In the alternating series, the positive terms is convergent, then that alternating series is called as an absolutely convergent. If a series n is equal to 1 to infinity Un containing both positive and negative terms, both positive and negative terms means it is in an alternating series, is said to be conditionally convergent if the series n is equal to 1 to infinity minus 1 to the power of n minus 1 into Un. This represents the alternating series, is a convergent, and absolute series is a divergent. Absolute series means it is in a positive terms. So conditionally convergent means an alternating series is said to be conditionally convergent. It satisfies the two conditions. What is the condition? The alternating series is in a convergent and the absolute series is in a divergent. This is an example for absolutely convergent and conditionally convergent. Some important theorems. Every absolutely convergent series is a convergent. But here, every absolute convergent series should be a convergent, but convergent series is not a absolutely convergent. Second one, if summation n is equal to 1 to infinity, un is an absolutely convergent series, then the series of its positive terms and the series of negative terms are both are convergent. If summation n is equal to 1 to infinity un is in a conditionally convergent, then the series of its positive terms and the series of negative terms are both divergent. Thank you.